Okay, hello students. Hello.
Yes, sir.
Okay.
Yes, sir.
Chalo.
Okay, thank you. So, can you people see the board?
Yes, ma'am.
Okay, fine. Yeah, I'm sorry. Yesterday I couldn't take the class because there seemed to be some problem with the connection. So at that time I could not take the connection. And before I forget, so I'll take instead of because we didn't have class yesterday, and so I'll take a class on Saturday at 11 o'clock. Is that okay? Saturday class at 11 o'clock. Is that all right with all of you?
Okay,
Okay, ma'am.
Okay.
okay, ma'am.
And also because I think we are supposed to finish teaching by 24th of December. So Monday, Tuesday, Professor Kulkarni, Sailesh Kulkarni used to take your class from 9:30 to 11, right? So instead of him now, I will take from 9:30 to 11. So Monday, Tuesday, although we are not scheduled, I'm going to take from Monday and Tuesday from 9:30 to 11, and then Wednesday, Thursday, and Friday I think is not there. So Wednesday, Thursday from our usual time, 11:15 to. Do you have any other slots which I can take in that next week? I mean, has anybody else finished the course so that I can take say 2 hours on say Wednesday and Thursday?
Ma'am, we have STQM internal on Wednesday.
Exam, is it?
Yes, ma'am. Ma'am, it's a request that instead of taking it on Monday and Tuesday, can you extend the hours on today or Saturday itself so that next week will be free for the revision?
No, the thing is today I can't take because I have got to do other works today. Means I have some other work in the afternoon also, and after 12:30 I have to go. I mean, there are some other things. So tomorrow,
Ma'am,
Huh?
how are you going to take from 9:30 to 11 o'clock in Monday and Tuesday? Because Monday and Tuesday we are having lectures. From 10 to 11 we are having MAP.
MEP, is it?
Yeah.
But MEP people, do they do MEP too? Okay, so MEP and MCP. Okay. I see. But what Sailesh was telling was that he was taking from 9:30 to 11 on Monday and Tuesday.
Ma'am, that was on Thursday and Friday, 9:30 to 11. And on Monday and Tuesday, sir was taking Kolikar sir's schedule. That was from 11:15 to 12:30.
Okay, so can I take that? Okay, you don't want on Monday, Tuesday because you have exam on Wednesday, is it? But okay, I will tell you tomorrow then. So tomorrow, okay, tomorrow I can extend my class definitely. So till what time do you want me to take? When do you want me to start and when do you want me to finish? You tell me for tomorrow.
Ma'am, we can start early as we have our STQM lecture from 12:30 onwards.
Okay, so what time do you want me to start tomorrow? Because I don't know what is your schedule now, because everybody's, I mean, we are not, I don't think people are really following a very fixed timetable as such. So you tell me what time is free for all of you, which is convenient for everyone.
Ma'am, is it okay from 10 or 9:30 to?
No problem at all. I can take from 9:30, sure. So 9:30 is fine for everyone tomorrow?
Yes, ma'am.
Okay, so from 9:30 tomorrow, okay? And next week I will fix, I mean, I will fix it tomorrow because I will talk to your other teachers and then we'll fix it. Because the trouble is, you see, I need at least, today I'm going to start group theory, so I need at least about 6 to 8 lectures. So unless I get that, I mean, we cannot, even if I just want to introduce the idea, something we have to do. And Friday is a holiday because of Christmas, 25th. So next Friday, then exams, I think back, I'm not very sure whether, have you people got the exam schedule already?
Yes, ma'am.
The
Yes.
final exam schedule?
Yes, ma'am. Ma'am, we have exams from 26th. 26th is skill management, and then from 28th we have regular subjects, and on 23 we have STQM internal, which was pending.
I see. 28 you have regular subjects, is it already? So when is your MMP?
Ma'am, MMP is on 31st.
Oh. MMP 2.
Yes, ma'am.
Okay, so let me do whatever we can let me do now. So, so far I talked about tensors. I mean, I did that to some extent, I think, in some detail. And in the process, I mean, I've often used these words of symmetries. Like, for example, the end we talked about, like, suppose I have the moment of inertia axis. It turns out that you have degeneracy for the principal axis. Then in that case, or if I look at the eigenvalues, if there's a degeneracy, then what we found is it means that there is a axis around which the body is symmetric. Or if you rotate about that particular axis, then I'm not going to get an angular momentum. Or I will get an angular momentum, sorry, which is parallel, which is proportional to the rotation frequency. So, and in another place also, I often said, I use this word symmetry, and we said that, or I mean, I often said that when I want to use tensors, then it becomes particularly very useful when I want to discuss about symmetries. So, what does one really mean by symmetry? Okay, symmetry, if I look at it as a word, then it really comes from a Greek word. So, you have metry here and you have sym here. So, metry is something to do with measure. This is metros is measured actually in Greek. That's why when we have metric tensor, I told you that it's a measurement of distances. And sim simply means something which is like, or in other words, something which looks identical, which have similar. So the parts look similar, or if I do something to that particular object, then it looks similar. So that's what it means. I'm just telling you the meaning, because often what happens is if you have some intuitive meaning, then you can understand what it is. Now, mathematically, what it means is that, suppose I have, for example, let's say I have this, say a set of masses, all are equal masses, and let us say I've arranged them at the vertices of an equilateral triangle. So, they are identical masses, all of them have the same mass m, and A, these are the vertices of some equilateral triangle. I've used the same alphabet A because to tell you it's identical. Now, what you can see is that, suppose I take this, and let's say this is my axis, and say I rotate this about this axis by 120 degrees, and this is going to go here, this is going to come here, this will come here. And it will look exactly the same. So, I'm making this rotation transformation, and your body looks exactly the same. So, mathematically, when I say symmetry, it means that I do some kind of transformations. So, this is, for example, here a rotation transformation about this axis, which is placed here at the centroid of this equilateral triangle, normal to it, and I rotate by 120 degrees. On the other hand, if I rotate by some other arbitrary angle, it is not going to look identical. And another example is, let's say I have this, say I have two masses put like this, identical masses. And let's say this is the central point. Now you can see that suppose I reflect about this central point. So I take I consider the plane which is normal to this, and then I reflect about this. Then you can see this will go here, this will come here, and again the system will look identical. So when I talk mathematically, when I say that some system has some symmetries, what it means is that I can do some kind of transformations on that system, and these transformations will leave my system invariant, or the body will look, or when I say invariant, in this case we are actually talking about the physical system itself remaining invariant. Now, why are we interested in studying such things? Now, it turns out that, okay, so now let's assume that, for example, this could be a spring, a mass with some springs here. So I'm having some spring here. And typically, what would I do? Or let's say even here. So let's assume now that these are masses which are connected by some springs. So, but once I have springs, what can happen to this system? This can vibrate because the spring can stretch or it can compress, so you can get vibrations. So I can get vibrations along this side of the triangle, or this side of the triangle, or this side of the triangle. And then the question I can ask is, what are the normal modes of these vibrations? All right. So now if I look at the normal modes of the of these vibrations, so you can actually construct the matrix, which this is something you might have done in classical mechanics, I think. So you can construct the matrix which is going to, so basically write down the equations of motion for these vibrations. It's essentially three simple harmonic oscillators. You can think of this as a harmonic oscillator, another harmonic oscillator, another harmonic oscillator. Write down the equations of motion for this and find out what are the normal mode frequencies. And once I have such a symmetry, what you will find is that the normal modes will be degenerate. So if I get so now I can reverse this argument and say that suppose I do some kind of a measurement on some system and I find that the normal modes of the world. So now think of this. And now let's try first plot of this as classical system with masses and springs. Now assume that these are some atoms. Okay? And there you don't really have springs, but you think that these are bonds. So the or lattice, so the atoms are sitting on some lattice which is like this. But you know that the atom, I mean, equilibrium position is this. So these equilibrium positions are this A here, the vertices of this equilateral triangle. But actually there will be fluctuations, so the atoms will vibrate. And again, these vibrations, so the lattice vibrations, these now all this is lattice vibrations, can be modeled by such springs, and the vibrational modes now actually will, I mean, why will these vibrations come? Because of the existence of phonons. Now, again, this is something you might have studied in solid state physics because here you can think of this as an elastic medium. So there will be these vibrations, and essentially the phonons which are responsible for this. But there now I can do measurements on these vibrational modes, and if I find that I have these normal vibration or the normal modes of the vibrations are say degenerate, then what it will tell me is that, or what I can get from that is my structure of my this material. So if these were certain atoms, and if they were placed in such a lattice, then by looking at the vibrational modes, or in other words, if I do a spectroscopic experiment, say a Raman spectroscopy, then from the Raman spectrum, what I can figure out is what is the lattice structure. Okay. And if there are symmetries, then there will be very definite patterns to what you would expect from the spectroscopic measurements. And now a formal way of studying these kind of symmetries and I mean, what are the kind of transformations which will leave these things invariant is through what is called as a group, the study of groups and representations of groups. So I just told you this in words so far that I mean the idea of these symmetries can lead us to an understanding of what is going on in the microscopic structures or even sometimes microscopically. But formally, if I wish to quantify these symmetries and quantify these ideas so that I can predict, or sometimes I can, given an experiment, I can figure out what it is, then I would actually mathematically study groups and representations of groups. So now, before I get into this, so groups is essentially some kind of mathematical structures, and representations are mathematical structures associated with groups. And these are, I mean, I can say that these are now ubiquitous. For example, I've already given you that you need this in mechanical systems. In quantum mechanical systems, for example, if I have a molecule, so a molecule, or if I have some material, then let us say that I have two atoms, say A and B. And then I ask whether such a, and let us say that the electron in this atom has a wave function, say some psi 1, and let us say that this wave function here. So if they are very far apart, the atomic wave functions here are psi A and say psi B. Now I can ask whether they will form a bond or not, a chemical bond. Now a chemical bond may be formed only if, say, for example, psi A and psi B transform under some particular representations of a group. Okay, so whether chemical bonds can form or not, and then if you want to ask, say, for example, look at this molecule. Let's say I have this. So let's say this molecule is this is carbon and this is this. Okay, so this is CO. Now, by looking at the symmetry structure of this, and let us say I have this molecule, O3, let's say, ozone. So these are oxygen molecules, or sorry, oxygen atoms placed like this now. By now looking at the symmetry of this vis-a-vis this, one can predict now whether this is going to have. So you can show, for example, that carbon of CO2 will not have a permanent electric dipole moment, whereas this ozone will have a permanent electric dipole moment. And how do I predict this? By looking simply at the expectation value of the dipole moment operator. Because this is now I have to use quantum mechanics. So I simply look at the expectation value of Qx. So it's in some particular state, and I look at this. Now here I can see that if I take inversion symmetry, this is symmetric under that, under inversion or under parity. On the other hand, this is not inversion under parity. Sorry, this is not symmetric under parity. So if it is symmetric under parity, then I can say that this expectation value should vanish. So if this expectation value should vanish, then what it tells me is that it cannot have an electric dipole. On the other hand, here I can't insist on, and I cannot say that it will vanish. And in fact, it will turn out that O3 will have a permanent electric dipole moment by carbon dioxide. So, a lot of, very physical properties of systems can be simply understood by looking at symmetries and their associated groups and the representations. So, what I'm going to do in these remaining few lectures is that, obviously, this is something which actually requires perhaps even if you really want to learn in detail, you should require perhaps one semester course, but we don't have that luxury. So, what I'm going to do is I'm going to actually just give you briefly an idea of what is groups, at least some brief definition of a group and some basic examples of certain groups. If at all time permits, maybe I will just touch on what we mean by representation. I'll just touch on it. I won't be able to do anything more than that. But if all of you are willing, then I don't mind continuing this after the exams and maybe another 10, 12 lectures on representations. Because unless you do representations, you really will not understand what one is attempting to do with group theory. But as I said, I don't want to do it in some hodgepodge way, and it's simply not possible now to do it in 6 lectures. So what I thought was best thing is that I do give you the definition of groups and also some other defining properties of groups in this 5, 6 lectures. Maybe just one lecture if I can. I will try to talk a little bit about what we mean by representation, and continue with this if you are willing after the exams. So next semester also I can take some. Even if people are interested, then I can take the interest lectures on representation, because unless you do representation theory of groups, as I said, the real flavor of this course will not come out. And especially for those people, well, it's useful for everyone. Even those who do chemical material science, because as I said, for chemical physics, if you want to figure out whether a particular molecule whether a particular chemical bond will form or not, you need no representation theory. If you do spectroscopy, so again there the selection rules are very much dependent on representations and so on. So whether you are an experimentalist or whether you are a theorist, if you want to understand microscopically and you want to understand better physical properties of materials and various systems, then I think we need more representations, really. And of course, for those of you who do relativistic quantum mechanics or relativistic field theories and astrophysics, then it's inevitable that you require group theory representations. But let me just here start, as I said, for now I'm just going to do some definitions for groups. So right now, I'll just talk about what as a mathematical property on how do I mathematically define groups. All right. So by group, what we mean is, so suppose I have a group G, then essentially it is a set of elements. Right? So I have a set of some elements. And let us say I denote the elements, let's say I will denote it as G1, G2. Okay, or maybe, yes, denote it as. So it is some set of elements. And then in addition, what I have to do is I have also to associate with every pair. So let us say now I have 2 elements. Instead of using G, let's use So let us say that I take G1. Instead of using G, let's use G1, G2, let me use H. K. Okay, let's use this. Now take some pair of elements in this. So let us say I take G and H. Okay. And with this pair, I associate some operation. So which I am denoting is with a dot here. So I associate with the pair GH. So associate with this a group operation, which I denote as dot. Okay. And once I associate this, so that means I've taken this particular pair and I have to order it also. It's an ordered pair actually. So G with H, and I do something to this pair, and that operation must satisfy the following properties. So the first thing is that, so if your G and H belong to G, then whatever I do, this group operation, it should also belong to G. So what this means is that the closure is what is known as a closure. Since you people have studied the definition of vector space, you can actually look at how this definition will do parallel that of for a vector space and how where it differs from a vector space. Okay. So for any pair, okay, so for every pair, so this is for every pair GH belonging to G, GH must belong to, or G dot H belong to G. And then the next part is that associativity property is satisfied. So whatever is your group operation must be associative. That means now I take GHK. So first I combine H and K with this group operation, and then after that I combine whatever is the resultant of that with G, and that should be the same as first combining G and H, and then combining it with. This is for every G. This is for every GHK belonging to G. So the associativity property must be satisfied, or the associative law must be satisfied. Then your group must have, there must be at least one element there. So there exists a unique element. So that means one and only one element. Let me call it as I, such that so for every G belonging to G, I must have some element, one particular unique means that there's only one element I, such that when I combine G with I must get back G, or I can do it in the reverse order, that I with G will also be G. Okay. And what we will call is I is known as the identity element. So I will be known as identity element of G. Okay. Or in other words, your group must contain a unique identity such that any element of the group combined with the identity gives me back G, and it doesn't matter whether I combine it from the right or from the left, I get back the same. Finally, for every element, okay, there exists a unique element such that So I can associate with every element G of the group of that set of elements another element H, which is unique. That is only one element H, such that when I combine H with G from the right side, then I will get the identity. And otherwise, I can also combine it from the left side. Then also I will get that. And then H is called as the H, which we will denote as. Okay. Is known as the inverse. So given an element G, I should be able to find the element, inverse element for that. And whatever it is, say this, by the way, this G inverse simply means it's a simply, that's why I've written it very inverse. It is simply denoted as G inverse. It doesn't mean 1 by G. Because so far we have now told you what is this operation, what are these set of elements. Now let's, before I go further, let's now talk about some examples of. So any set of elements which satisfy this, any set of elements and a particular operation group, what we call as a group operation, and in such a way that 1, 2, 3, 4 are satisfied, if I can do that, then that's called a group. So let me consider now this set. So consider this set. Okay, so this is a set with 2 elements. Okay. And let us define group operation here as multiplication, as ordinary multiplication. Okay. So in this case, you have a set which, so let's call this G1 as -1 and G2 equal to +1. So now you can see that if I take G1 with G1, so the group operation is, so it's like -1 times -1, and this is equal to 1, and 1 belongs to 2. So if I consider this is my group here, under group operation, it is simply ordinary multiplication. If I take G1 times G1, I'll get +1. So therefore, it's belonging to G. Similarly, if I take G1 times G2, so in this case now it's -1 to 1, but this is equal to -1. This again belongs to G. And if I take G2 with itself, that is 1 into -1, which is equal to -1 belongs to G. And I should take one more because you see, when we have written it, the ordering is also important. We'll see why that is true, right? So I can also take G2 with G1. So this is equal to 1 with -1, and that's again -1. So closure is satisfied. You can verify for yourself that, so this first property is satisfied. You can verify that associative law is satisfied. And you can also verify for yourself now the third one, that there is an identity. Because you can see from this already that -1 into 1 gives me back -1. 1 into -1 gives me back -1. So my 1 is the identity element. You get 1 into 1. This is 1 into 1. So 1 into 1 again gives me back 1. So 1 is the identity element. And further, you can also see that from here, for example, you can see that what is it? So from here you have to look at what is the inverse now of -1. Does an inverse exist? Suppose I take the element 1. What is the inverse of 1?
And 1.
1 itself, very good. And what is the inverse of -1?
-1.
-1. So you can see that the inverse of -1 therefore is -1 itself. It's not 1 by, yeah, in this particular case it's multiplication, so it's actually -1. Right? So the inverse also exists and it's a unique inverse. So all these 4 properties are satisfied. So this forms a group. And by the way, this is called as the set to group. So this is an example of a group. In fact, I could think of this as a simplest example of a group. Trivially, even if I just take one, that also is and if I use multiplication, that's also, but that's a very trivial example. Now another example which I could take is, consider this example. So this is one example. Consider now this set of all integers. Okay. And your group operation is addition. So again, you can see that if I take two integers, let us say I have integer I1 plus I2. Okay. So let I1 and I2 belong to G. So they are two arbitrary integers. Then you know that I1, okay, so I1, this is by definition, I1 plus I2 because I've taken the operation this. But if I add two integers, then you know that again it will belong to G. Because again there is an integer. So closure is satisfied. Similarly, you can show that the associativity property is satisfied. Okay, what is the identity here? Element. Can I find a unique identity element here under this? Does there exist an identity here?
Ma'am, identity element is 0 under addition and it is an integer. So
So identity exists. Identity element exists. So unique identity element exists. Equal to 0. Because you know that I1 plus 0 equal to I1 equal to 0 plus I2. What about an inverse for every G or for every I belonging to?
yes, ma'am, it will exist.
What is the this thing? What is the inverse now? So what is I inverse now?
Minus of 5.
Minus. Okay. So you can see that this is equal to minus. Because I1 plus minus I is equal to minus. So therefore what you can see is again that those four properties are satisfied. So closure associativity is because addition is associative. Associativity is always satisfied. So this set of all integers therefore with group operation is identified as ordinary addition is a group. So for any group, what we need is therefore we need to define a set of elements and then I have to define their appropriate operation. Now let's do another example. Consider now the set of all. Okay, let me take G to be the set of all 3 by 3 of modules. And next the group operation B. Matrix operation. when I say that G is a set of all orthogonal 3 matrices, 3 by 3 orthogonal matrices, what does one mean? That G is a set of all matrices R, set of all M, where M is a 3 by 3 matrix such that if it's orthogonal, what does it mean?
M inverse equals M transposed.
Yes. So, by definition, okay, so it simply says M transpose M equal to identity equals to M. And when I say it's orthogonal, it also means that these are real. Okay, if you want, I can actually put real. I mean, this is redundant, but I'll just put. Okay. So, I consider now the set of all such matrices, 3 by 3 matrices, such that this is satisfied. That condition is satisfied. And then now on this, I'm defining my group operation to be so all M. Okay, so let's say write it as all M such that. And now I'm saying that I'm going to define the group operation to be an ordinary matrix multiplication. So if let's say that I have two matrices which both are orthogonal. So is the closure satisfied? Because now the group operation is simply multiplying. Suppose M1 is an orthogonal matrix and M2 is an orthogonal matrix. So is M1 times M2, where M1 times M2 is simply matrix multiplication of M1 and M2, is that orthogonal? See, because if, okay, how will I prove it's group? How will I show that this is a group? Okay, I'm claiming now that this is a group. Okay, how does one show the group? No, that is a group. So first thing to do is that given two arbitrary elements, I have to show that if I combine these two arbitrary elements using this group operation, then that combined object also belongs to the group. So suppose, okay, so check closure, okay, first. Okay, so let M1 belong to G. What does this mean? It tells me that M1 must be an orthogonal matrix. So this means that M1 transpose M1 should be equal to identity M1. Fine. Similarly, let M2 also be another matrix belonging to G. So it tells me that M2 transpose M2 should be identity. So this is by definition. Because all these such matrices are belonging to this set. Now I take the combination of M1 times. This is the group operation, which is nothing but multiplication of these two matrices. Now I'm multiplying two matrices, 3 by 3 matrices. I know how to do the matrix multiplication because we've said that this group operation is simply ordinary matrix. Now what I need to check is whether this object belongs to this set or not. When will it belong to the set? See, the combined object is M1 times M2, which is simply the multiplication of matrices M1 and M2. When will it belong to that?
If this is identity.
Why identity? See, I have combined M1 with M2. I've got another matrix. See, if I combine two 3 by 3 matrices, I will get another 3 by 3 matrix. That is for matrix multiplication. Now, I have to check. Closure means I have to check whether this object belongs to this set or not. Now, what does that set contain?
Yeah, so M1, M2 acted on M1, M2 transpose should give us identity.
So I should check whether M1 and M1 times M2 is orthogonal or not. That is what I need to check. Because if M1, M2 is orthogonal, then it will belong to that set. You get it? So check whether M1, M2 belongs to G. Okay. So how to check whether that is there? So I have to check its orthogonality property. So check whether M1, M2 transpose M1, M2. What is this value? Now what will this be by definition? I should show that this should be equal to the identity, because if it is equal to identity, then I can say that this is M1, M2, whatever that matrix is. So let us call this let. Okay. So M transpose M equal to this, it is this. Okay. But what is this equal to?
Identity times identity.
From M2 transpose.
So this is going to be M1 transpose, M1 transpose, M1. But because M1 is orthogonal, this is identity. So this is going to be M2 transpose identity M2. And see, here I'm using all our matrix multiplication. So therefore, what you can show is that M transpose M is identity. And similarly, you can show M transpose is. So in other words, this combined M1, M2 is again an orthogonal matrix. So what this shows is that M is orthogonal. M is 3 by 3 matrix, orthogonal matrix. Because obviously I'm combining 2 or multiplying 2 3 by 3 matrices, I'm again going to get a 3 by 3 matrix. And therefore, so this therefore implies that M belongs to G. Because according to us, our G is the collection of all possible M such that the orthogonality property is satisfied. Correct? So therefore, what you can see is that if I define my G now in this fashion, this set is again a, with the group operation being defined as ordinary matrix multiplication, is again a. Okay, by the way, where did we encounter such things? Did we encounter such things somewhere? I mean, did we encounter such matrices anyway earlier? Have we encountered in our lectures at least any 3 by 3 real orthogonal matrix?
A rotation matrix.
Rotation matrices. So this is actually nothing but the set of all 3 by 3 rotation matrices. So that's how we define our rotation matrix. Or in other words, what we are showing now is that, okay, you can, I've shown only the closure here, but what you can do is, okay, so closure is satisfied, okay. Now, of course, you should do further. Oh, yeah, I forgot. So my closure is satisfied, okay. Now use you can show that the associative law will be satisfied, verify, okay. Use matrix multiplication, you can show that associative law is satisfied. Then the next thing is to ask, what is the identity element? What will be the identity element here? Is there any identity element here such that if I multiply any element in G with that matrix, I should get back the matrix itself?
Identity matrix itself.
Identity element is a 3 by 3 identity matrix. Because you can see that identity matrix anyway will satisfy this condition. Because I transpose I will be equal to I. Okay, so there exists a unique identity element. And what is the inverse given in?
M transpose.
There exists a unique inverse M inverse, which is equal to M transpose. And you can also see that if M is orthogonal, M transpose is definitely orthogonal. That's belonging to G. So therefore, you can see that all the 4 properties of defining properties for a group is satisfied under these conditions. So the set of all, therefore, this simply tells you that G is a. And as I said that you have already encountered such matrices. These are nothing but your rotation matrices, 3 by 3 rotation matrices. So what this is really telling you is now that the set of all 3 by 3 rotation matrices forms a group. And that particular group will give a, this is called the O3 group. This is known as the O3 means, say this 3 stands for 3 by 3 matrices and the O here stands for orthogonal matrices. So it's a collection of all 3 by 3 orthogonal matrices. And what we saw later, now a little bit more. Now you can ask, we saw that when we talk about rotation matrices, now from here, again you can see from this definition, that determinant of M equal to plus minus 1. From here we've seen this. Because we saw this in our rotation matrix, R transpose R equal to identity, then it tells you immediately that determinant of R can be plus or minus 1. And so if I consider now determinant M equal to plus 1, now how did we, so let me just restrict to those matrices M such that determinant of M equal to plus 1. Now if you go back and remember of your rotation matrices, how did we specify an arbitrary rotation matrix? We said that we can specify an arbitrary rotation matrix in 3-dimensional space. Here I'm talking 3. How did we specify? Do you remember? What are the various quantities? See, I go back to the, remember that. So we had a space, we had x, y, z axis, and then I would make a rotation like this, suppose I make rotation. So if I want to specify some arbitrary rotation transformation, it will take me from x, y, z to x prime, y prime, z prime. How many parameters did I require to specify this? Nobody is able to say? Okay, when I specify a rotation, what do I do? Basically, what do I do?
And first we fix the axis of rotation.
Yeah, and then?
And the parameters that are changing.
No, you fix an axis, so I have to rotate about a particular axis, and then what other thing I have to specify? How
and
much
the direction.
No, when I specify the axis of rotation, I'm specifying around which axis I'm doing the rotation. But then I have to say how much I'm rotating about it. So the angle of rotation. So I need to specify an axis of rotation in cap and how much I'm rotating about this in cap axis. So for example, I'm rotating about the z axis. So I specify the z axis. And then in the xy plane, how much angle I'm rotating. So for example, so if I let us say I'm rotating about the z axis, then I have to tell you that xy. Now I go to from xy to some xy and y prime, and I go by an angle phi. So this is phi, and then n cap here will be the z axis. Okay. So the angle of rotation or the angle by which I'm rotating, and this n cap. Now n cap is a direction. So to specify the n cap, how many parameters do I require? If I want to specify a direction in my space, how many parameters will I require? We have done this. No, for a direction. We have done this in the beginning. That time I said I'm going to use it again, but you people said you have forgotten. If I just want to specify n cap, an axis of rotation. Okay, suppose I want to specify my x-axis. How will I specify the x-axis?
And by I vector.
Yes, I vector, but I wanted to say, okay, so I vector. So for I vector, how many, okay, if I want to specify a vector, how many components do I require?
3.
Again, 3 components. But now this is a unit vector. If it's a unit vector, then how many independent components do I require?
1.
How 1? See, 3 components. So any arbitrary vector, if I want to specify, I need 3 components. And let us say the components are x1, x2, x3. Okay. If it's a unit vector, what does it mean?
All are 1.
All are 1. When I say a vector is of unit magnitude, what does it mean? What if I say it's a unit vector? I cap is a unit vector or not?
Yes, ma'am.
What are the components of I cap?
I'm 1, 0, 0.
So all the vectors are all the components are 1. So when I say something is a unit vector, what does it imply?
Its mod is 1.
Magnitude is 1. So when its magnitude is 1, what does it mean? Suppose I have vector now x1, x2, x3. When I say its magnitude is 1 or length is 1, what does that mean? When I say the length of the vector with these components is 1, what does that imply? Okay, what is the length of this vector? Given a vector has these components, what is the length of it?
x1 square, x2 square plus x3 square.
Now, what is that? x1 square plus x2 square plus x3 square. But is that the length? Length is what?
R square. R square.
That is length square.
Under root of x1 square, x2
So the
square.
length of this vector is root of x1 square plus x2 square plus x3 square. And if I say that the length must be equal to 1, what does that mean? This should be equal to 1. See, when I say something is a unit vector, it means that the length of that vector is 1. Or in other words, it tells me that root of x1 square plus x2 square plus x3 square should be equal to 1. Now, given that your components x1, x2, x3 satisfy this condition, how many independent components do you have?
2.
2. So therefore, if I want to specify an arbitrary unit vector, how many components or how many parameters do I require?
3.
I want to specify an arbitrary unit vector.
I'm
That means
2.
a vector. How many?
I'm 2.
2. Because you see, the length is already specified. If you want to specify an arbitrary vector, then you need 3 components. But if I want to specify an arbitrary unit vector, when I say it's a unit vector, it means it's a vector of unit length. Unit length means x1 square plus x2 square plus x3 square. The square root of that is equal to 1. But this tells me that all 3 cannot be independent. One of them must be dependent on the others. So I only have 2 independent components. That's why when I say that the axis of rotation n cap, it's n cap when I write it's a unit vector. N cap dot n cap equal to 1. So when I want to specify the axis of rotation, I only have to specify 2 independent parameters. Or because see, it's enough for me to specify it for a direction. I don't need the length of the vector. I just need to specify the unit vector along that. So if I want to specify along x-axis, it's enough to specify I cap. Okay. So therefore, I have 2 parameters here, 1 parameter here. So 2 plus 1, 3 parameters. And there's something which we did right at the beginning. That an arbitrary rotation matrix for 3 by 3, you need 3 real parameters to specify. Alright. And what you can see is now from here that these 3, so that means if I go back to this group, any element of this group here, n, forget for the minute this minus I, can be specified by n cap and phi. And phi is now continuous parameter. For example, the angle I'm rotating, it's going from 0 to 2 pi. Because if I rotate about the z-axis, then I can rotate from 0, about say pi by 3, pi by 4. Continuously I can change from, so for example here, you can see that I can rotate about this by pi. Pi can vary from 0 to 2 pi. It's a continuous parameter. Similarly, your direction in space. Again, that can be specified by 2 parameters, which are continuous parameters. In fact, what I can use is if I go to spherical polar coordinates, I can use the theta phi there. So, therefore, what you will see is that an element of this group, an arbitrary element of this group, can actually be specified by 3 continuous parameters. Okay. So, let me again summarize what we did so far. So I'll just remind you of all the 3 different groups we had. So one group which we had was -1, 1. The first example I do. Let me give a name to this. I'll call this as grade 2. Okay. Then we had this other group G1, which is the set of all integers. Okay, with finally this G equal to O. Okay, with matrix multiplication. Right? So these are the three examples I chose. Now you can see that this particular group has only two elements in it. Right? Only -1 and 1. This group has the set of all integers. So it's from say 0, 1, 2, 3, 4, 5, 6. I can count. And similarly, I can count from the negative matrix. Here again, this is a set of all matrices such that M transpose A is identity. And what we have also seen is, you can see that I can specify matrices, also the -1s. I told you that for the rotation actually. Most generally, I can specify by a member with determinant of R equal to +1 times that parity transform matrix. So I have matrices which can be specified by 3 continuous parameters, or a 3-parameter group. By any group element can be parameterized by 3 parameters, which are continuous parameters. So I have these 3 different groups. So now this here I have group. This is an example of a group where you only have finite elements. Because I just in this particular case I don't need. Now this is an example of a group where you have an infinite number of elements. Because you're taking the set of all integers, obviously you have an infinite number of such elements. Again here this is an example of a group which has an infinite set of elements, because you can see that O3, I have an infinite number of such matrices which will satisfy this condition. Okay. But the difference between these two, what is the difference between these two? Here I can count. Because I can say like I1, I2, I3, 1, 2, 3, 4, 5, 6. On the other hand, here, the elements I can't count because they are actually parameterized by continuous parameters. So what we can actually do is we can classify groups now into two types. So this I define for you what is group, and then we also I given you some examples of groups and check for you how, or at least show you how to check whether a particular set with a particular group operation is a group or not. And then further, we will classify groups into some classes. So I will call a group as finite group is a group with a finite number of elements. So by definition, if my set has a finite number of elements, then that is a finite. Then I can have infinite groups where the number of elements are not finite. So it's an infinite number of elements. Okay, that's an infinite. And infinite group, again I can have, this is an example of an infinite group, this is an example of a finite. And this further I can have, it's called as a continuous group. Okay. So a continuous group is a group with elements specified by continuous parameters. By continuous parameters. So for example, we saw that I told you that we can specify O3 by parameters n cap and phi, and n cap is an direction, so that can be specified by 2 continuous parameters, and phi, the angle itself, can be specified by another continuous parameter, and therefore it's a 3-parameter group, continuous group. So again, like once I have a group, then I can classify groups into finite groups, and infinite groups further can be classified in terms of continuous groups, and these are numerically infinite, countably infinite. Yeah. But anyway. Right? Further classification is the following. So these are some normal classifications. Now again go back to this Z2 which I defined. So let's consider Z2. I shouldn't have removed that. So Z2 is -1 to 1. Okay. So let me take these examples. So G1 was a set of all integers. I should not have removed this. See, when I say O3 group, the group operation is matrix multiplication. That is specified already. Okay. Now again, you look at this here. Now if I take the element here -1 times 1, this is equal to 1 -1, which is also equal to 1 into -1. So you can see that if I take two elements here, any two elements, and multiply them, it doesn't matter in which order I multiply, I get the same answer. Because ordinary multiplication, you know, is commutative. Similarly here, if I take two integers and add, so I take say I1, I2. If I take I1 plus I2, I will get an answer, which is some I3. But this is the same as I2 plus I2. So whether I combine I2 with I1, whether I combine I2 with I1 or whether I combine I1 with I2, I get the same answer. But now look at O3. Suppose M1 is one matrix and M2 is another matrix, which I've satisfied this orthogonal before. I get M1, M2 when I multiply this group operation, matrix multiply. Now I do the other way around, M2 with M1. Will I get the same answer? Instead, what do you expect?
No, ma'am.
Why won't you expect? Yeah, go ahead.
Ma'am, because matrix multiplication is not associative.
It is not associative, it's not commutative.
Sorry, ma'am.
It's not commutative. Okay. So this in general is not equal to M2 times MC. On the other hand, what you will see is that these two examples, so therefore what you find is now that I can distinguish groups depending upon whether the group, when I combine them to the group operation, whether that group operation is commutative or not. Okay. So now let me define it for you. So a group G is said to be, so this is some jargon, but that's all it means. It's said to be abelian. You see? So it's an abelian group if any two elements okay. So this is for any two arbitrary elements. Okay, because you see, for example, here, if I take M2 to be identity, then of course this is true. But for any two arbitrary elements of the group, if I can show always that G with H, combining G with H is the same as H with G, where this is the group operation, then I will call this as an abelian group. Else, G is said to be non-abelian. So these two are abelian groups. So these two are examples of abelian group. And this is an example of a non-abelian. So abelian and abelian groups are a geometry law. Mathematician, what able. So it's up to you. Now further, I mean a little bit more about some definitions of groups. Now given a group, okay, so let me give you another example of a group. One more example I'll give you. So let me define another group, say 4 in the following way. So let's define it as 1. I is our imaginary I, okay, and with the group operation to be equal to 9. Again, you can see that if I take here 1 with I will get back I. If I take 1 with minus I will get back minus I. I with minus I will give me plus 1. Minus I with itself will give me minus 1. So you can see that under group multiplication or under the group operation, which is multiplication, ordinary multiplication, that this is closed. Further, what you can see is that associativity law is satisfied because multiplication satisfies the associative property. Then you can also see that you have the unique identity element, which is 1, which belongs to the group. And for also you can see for every element, I have the unique inverse. So for example, for 1, the inverse is 1. For minus 1, it's minus 1. For I it is minus I, and for minus I, the inverse is plus I. So therefore, this forms a group. Okay. So this is another example. Now look at the property of this group. Now from this, suppose I extract a part which I will define simply as 1 minus 1. So you can see that this is a subset of Z4. So I've taken this Z4 and then taken just 1 and minus 1. So this is some subset of this set. But you can see that if I take this subset and then if I define again dot as multiplication, that means with the same thing, this again forms a group. So this is again a group with group operation with multiplication, the same operation. So what you see is that this particular group has a property that one subset of this is again satisfying all the properties, because this subset is nothing but your Z2, as you can see here, satisfying all the properties of the group. So often it will happen, and similarly, for example, here. So here, for example, I had this is equal to set of all M such that M transpose M equal to IDC equal to M. Okay. Now consider a subset. Okay. So let okay, I'll call it equal to.
Excuse me, ma'am.
Yes.
Ma'am, we have another lecture now.
So what lecture?
MSTQM lecture.
Where is that being held?
Ma'am,
In the
it was
Raman.
supposed to start at 12:30, and sir is asking to join the meeting.
So it is in Raman Hall, is it?
Yes, ma'am.
Okay. Okay. I think I'll stop here. So tomorrow the class is at 9:30, right?
Yes, ma'am.
Ma'am, 9:30 to what time?
9:30 to?
What time? Till when?
Till when? Okay. Till what time do you want me to take? You tell me. You people tell me. 12 o'clock?
12 o'clock.
12 o'clock.
But we want breaks in between.
Okay, we'll take a break in between. Very good. We'll take a break. Fine, no problem. You're taking class here in Raman Hall. I know they told me. So, 12:45 also. They told me, I know that. So, where do I go?